Hello everyone, welcome back to the channel. In this video, we are going to discuss a GATE 2025 linear algebra problem and its solution. After that, we will see the core concepts involved behind the problem. And finally, we will tackle a few practice problems related to above concepts plus some practice problems for you to try yourself. So let's begin. So the problem is the sum of elements in each row of A, which is an n cross n matrix, is 1, which means A is an n cross n matrix, and sum of each row of A is 1. If B is equal to AQ minus 2 square plus A, that is B is also an n cross n matrix, which can be formed using this polynomial. Which of the following statement is correct for a vector x, which is an n dimensional vector? Okay, the options are equation bx equal to 0 has no solution, equation bx equal to 0 has exactly two solution, equation bx equal to 0 has infinitely many solutions, equation bx equal to 0 has unique solution. So let's jump to the solution. Now we have here given A is an n cross n matrix such that sum of elements in each row of A is 1, and given matrix B, which can be formed by this equation, we need to determine how many solution or solutions bx is equal to 0 have. Okay, so what we have is, we know if sum of each row of A is 1, then this vector, which is an one vector, so each element is 1, which is an n dimension vector, is an eigenvector of A corresponding to eigenvalue 1. Okay, which means here sum of each row of A is 1, which means this is an eigenvector of A corresponding to eigenvalue 1. Why? This we'll see. So let A is an n cross n matrix, okay, such that elements are a11, a12, or a1n, okay, such that the sum of each row of A is 1, and we need to show that the vector 111 n dimension vector is an eigenvector of A corresponding to eigenvalue 1. Okay, let we take this vector x, which is which consists of each element 1 belongs to is an n dimension vector. If we see Ax, then this is nothing but the matrix A with the vector x. If we multiply this, we will get is a11 into 1 plus a12 into 1 plus a1n into 1. This we will get as the first element. An1 into 1, an2 into 1, an into 1. This will get as the last element. Similarly, we will get this. Okay, but we know this is nothing but sum of each row of the matrix A. That is a11, a12, a1, sum of first row of A. This is sum of last row of A. This is nothing but, we have already seen that this sum of each row is 1, which means this is nothing but a vector of each element 1. Okay, n dimension vector. So what we'll get is, we'll get Ax is equal to this one we have taken into this one vector. Okay, this is an n dimension vector. If we see, we can write this Ax is equals to 1 into x, and this is nothing but, this is in the form of Ax is equal to lambda x, okay, which is the eigenvalue equation. Okay, so we'll get x is an eigenvector of A corresponding to eigenvalue 1. Okay, now hence we'll get this vector is an eigenvector of A corresponding to eigenvalue which is equal to 1. Okay, now we have given that matrix B can be formed using this equation. If we simplify this equation, we take A as common, then we'll get this. If we see this, nothing but A square minus 2ab plus b square, this is sort of this equation. Okay, then what we'll get is, we'll get B is equal to A into A minus I square. Now one note is, for any polynomial function of A, we can replace A with its eigenvalue lambda. It means if there is any polynomial of A, let's say A cube x, we can replace this A with its corresponding eigenvalue. Okay, why? This we'll see. Let P of A is an polynomial of A. Okay, then let x is an eigenvector of A. Then if we multiply P of A into x, then this can be written as this. we know that ax is equal to lambda x. This is the eigenvalue equation of a. If we see a square x, then a square x can be written as a into ax, and then ax is equal to lambda x, then a into lambda x. Okay, then a square x can be written as, if we take this lambda as outside and a inside, then we written as lambda into ax. Okay, lambda into ax, but ax, this is equal to lambda x again, then this can be written as a lambda square x. So ax is equal to lambda x. A square x can be written as lambda square x. Similarly, a cube x can be written as lambda cube x, and so on. Okay, then if we replace a cube x, a square x, and ax with its corresponding lambda x, lambda square x, and lambda cube x, then we'll get p of a into x can be written as this polynomial. Okay, here p of a is this polynomial is nothing but the b which is given. Then we can written as bx can be written as into this form. Okay, now because b is equal to this, so one more thing, if x is an eigenvector of a, then x is also an eigenvector of b. Why? Because eigenvectors do not change under polynomial operation. Okay, since we are applying any polynomial equation on a, and the eigenvector do not change under polynomial equation, so the eigenvector of a and b both will be same. It means if x is an eigenvector of a, then x is also an eigenvector of b. Okay, let's say mu is an eigenvalue of b corresponding to eigenvalue x, then we can write that bx is equal to mu x. Okay, because x is an eigenvector of b corresponding to eigenvalue mu. Here we can write as bx is equals to mu x is equal to, and here we have bx is equal to this. If we compare these two equation, then we'll get the eigenvalue of b can be written as this form, where lambda is an eigenvalue of a. Okay, this equation. Now we know that one eigenvalue of a is lambda is equal to 1, because sum of each row of a is 1, and then if we put lambda is equal to 1 in this equation, then we'll get one eigenvalue of b. Okay, then we get one eigenvalue of b is 0. It means the matrix b has 1 0 eigenvalue. Okay, and hence we'll get the determinant of e is equal to 0, because the determinant is nothing but the product of eigenvalues. Okay, product of if by an eigenvalue is 0, then the determinant of b is 0. And we know that for homogeneous system of equation bx is equal to 0, if determinant of b is equal to 0, then it has infinitely many solutions, which means the equation bx is equal to 0 has infinitely many solutions. Okay? And if we want to know the solution, then the solution is, we know x is an eigenvector of b corresponding to eigenvalue 0, and this is the eigenvalue equation. If we put mu equal to 0, then we get bx is equal to 0. Okay, where x is nothing but just the vector of all ones and dimension vector. It means the equation bx is equal to 0 has at least one solution, and the solution is this 1 1 1 vector. Okay, and since if we take any scalar multiple of x, that is if we take c into x, any scalar multiple of x, then this will also satisfy the equation bx is equal to 0, and hence this equation is infinitely many solution. One solution is this, and the infinity solutions are scalar multiple of this. Okay, now we'll see the core concepts that are involved in the previous question. This you can add in your short notes. These points you can add in your short notes. So first one is, if A, let's say, is an n cross n matrix, and sum of each row of A is small a, then we can say that the vector consists of all element 1 and dimension vector is an eigenvector of A corresponding to eigenvalue small a, which means this x is a whole one vector consists of each element 1 and dimension vector is an eigenvector of A corresponding to eigenvalue which is small a. Okay, and small a is sum of each row of A. Okay, second one is, if A is an n cross n matrix, and let's say p of A be a polynomial of A, okay, then we can replace A with lambda in the polynomial. Let's say p of A is a square minus a something this, then we can replace A with its eigenvalue lambda. Why? Because we have ax is equal to lambda x. We know a square x is equal to lambda square or a power nx is lambda power nx. This you can drive easily. Third one is, if P of A is polynomial of A, which is an n quotient matrix, and let B is equal to P of A, then eigenvalues of B can be find out by replacing B with eigenvalues of B and A with eigenvalues of A, which means, let's say B equal to A square minus A square plus A, then eigenvalue of B, which is mu, equal to lambda square plus lambda. This you can write down. Okay. And the fourth one is, let x be an eigenvector of A, then x will also be an eigenvector of any polynomial of A, which means, let's say we have a B which is a polynomial of A, which is equal to A square plus A. Okay, then then let's say x is an eigenvector of A, then x is also an eigenvector of P of A, which is equal same as B. Okay. Now we will see some practice problems which will help you to understand the concept in a much better way. So the problem is, given matrix C, which is a 4 cross 4 matrix. We need to find out, first we need to find out the eigenvalues of C. Second is C is diagonalizable. Third is equation Cx equal to 0 has no solution, unique solution, infinitely many solutions, exactly 2 solutions. Okay. So first we will see, we have to find the eigenvalues of C. So this is the C matrix given. If you carefully notice that sum of each row of C is 2, okay, then we can directly say one of the eigenvalue of C is 2, and one of the eigenvector of C is 1 1 1, which is a 4 cross 4, 4 cross 1 dimension. Okay, sum of each row of C is 2, that is, this is an eigenvector of C corresponding to eigenvalue 2. So one of the eigenvalue of C is 2. Now, if we see this matrix C, then carefully notice row 1 and row 3 are same, row 2 and row 4 are same. Okay, row 1 and row 4 are same. Then if we reduce this to row reduced echelon form, then we will get this matrix. Here, 2 of the rows are 0, which means the nullity of C. The nullity of C is 2, and hence and the rank of C is 2. Okay, nullity is 2, rank is 2, which means, since nullity is 2, which means 2 eigenvalues are 0. From this we can say that the 2 eigenvalues are 0, which means lambda 2 lambda 3 is equal to 0. Okay, now we can say that, and trace of C, which is equal to 0, because trace of C is sum of diagonal elements, which is equal to 0. Okay, and we know that lambda 1 lambda 2 lambda 3 and lambda 4 is 0. Since we know that lambda 1 is 2, then these two are 0 0 and lambda 4 is minus 2. So the eigenvalues of C are 2 0 0 minus 2. Now we have to find the C, whether C is diagonalizable or not. So one way to find it, we find the eigenvectors of C. Okay, if C has 4 linearly independent eigenvectors, then C is diagonalizable because C is a 4 cross 4 matrix. If C has 4 linearly independent eigenvectors, then C is diagonalizable. Okay. Another way to find is to find geometric multiplicity and algebraic multiplicity corresponding to each eigenvalue, and if geometric multiplicity is equal to algebraic multiplicity for each eigenvalue, then we can say C is diagonalizable. And these are two lengthy methods. Now we moving on to the shortcut method, which use spectral theorem, which is spectral theorem says that every real symmetric matrix, that is A equal to A transpose, this is the condition for matrix to be real symmetric, is orthogonally diagonalizable, which means there exists an orthogonal matrix such P, which means P inverse is equal to P transpose, such that A equal to PD P transpose, where D is a diagonalizable matrix. D is a diagonal matrix. Sorry. Okay. Which means if A is real symmetric matrix, then it can be diagonalizable, and D is the diagonal matrix. Okay, D diagonal matrix whose diagonal elements are eigenvalues of A. Here, if we see that these are 0 and C is a symmetric matrix. Okay, symmetric matrix which with all elements real, and hence C is a real symmetric matrix. Since C is a real symmetric matrix, which means C is diagonalizable. Okay, now we need to find how many solutions equation Cx equal to 0 have. We know rank of C is equal to 2, which is less than the dimension of C, which hence C has infinitely many solutions. One way to see is, we know two eigenvalues of C are 0. Two eigenvalues are 0, which means determinant of C is 0. Determinant is 0, and hence Cx equal to 0 has infinitely many solutions. Okay, so the equation Cx equal to 0 has infinitely many solutions. This is the problem number 2, which you can solve by yourself. So this given matrix, which is also a 4 cross 4 matrix, you have to find out the eigenvalues of C. Is C diagonalizable, and like how many solutions C equal to 0 have. And I have given the answers, which you can check from here. If you have any doubt or queries, let me know in the comments below. You can also join our Telegram channel for any discussion or to ask any query directly. And for more such content, don't forget to subscribe. Thank you.